All right, so let's go to the class site here. So basically we have this week and next week. Today we're going to finish up doing some matched pairs examples. This is kind of like our two population stuff. We'll then kind of move on to linear regression a little bit today. And we're basically doing that the rest of this week and next week. I will probably, depending on how quickly we go through the material, I don't know how much exam review we would have kind of this next Thursday. But I'll also be doing for my other sections that following Monday, like a review session on that Monday. So, you know, if we don't get a whole lot of review, I'll be posting those videos to the YouTube page as well to kind of get some additional review in. I'll also kind of make the link available. So if you do want to watch those live on Monday during my other sections while I'm doing some review, you can. And if I have any other kind of additional videos I'll post, I'll mention those next week as well as we get closer to that final. I put up some final exam. Oh, no, I didn't. I did for the other sections. I'll do it today. I did that for them yesterday. So it'll basically have two practice exams and the final exam formula sheet. Some of the stuff won't look too familiar because it's going to be kind of linear regression, which is stuff we'll be kind of continuing to work on. But in terms of all the two population stuff, that should be on there. Really, that's going to be what's on this final. So it's not going to be comprehensive. It's going to be kind of newer stuff. The content area will be kind of more limited. So it's not as spread out. You're really just focusing on hypothesis testing, confidence intervals for two population examples, and then we'll be focusing on linear regression here for the kind of remainder. Any questions from you before we get going? Okay, so we've been looking at two population examples, right? And this one's kind of like two population, but it's really, we can treat it like it's just one. So actually this matched pair stuff kind of gets a little bit easier than what we've been doing. So we're basically going to start out with, we really have one population. It's just that we are collecting data on them in two different time periods, right? Or on two different dimensions. So, excuse me, usually this is going to be a before and after. So it might be something like a manager wants to know, like after they change the layout of the workstations, did the productivity of their workers increase, or did it decrease, or did it change? So let me go to the dot cam here. All right. Ooh. Okay. So we kind of think about maybe we have different names of our employees. So John C, Mary S, etc. We would then have what their productivity was before, right? So maybe this is something like 10, 15. We then have a measure of what their productivity was after the change. And then what we're going to do is create a difference variable, right? So we're going to look at what was the change essentially in productivity. What was the difference between these two? So -2, this, went up by 3, so after minus the before. And we could do that for every single person. If we did that for every single person, we could then find what was the average change, or what was the average difference in productivity. So we're going to calculate this thing. Instead of calling it a sample mean, we're going to notate it as we're finding the sample difference, right? Because we're not just looking at one variable, we're looking at kind of this variable we created, which was the difference between two other variables. So it's really going to be the same process, though. We would find the mean the exact same way. It's just now, instead of calling it a sample mean, we call it the kind of sample mean difference, right? Just like when we had a sample variance with a sample mean, now we could also find the sample variance of this difference variable. So we're going to call that just the variance of that difference variable. Okay. So that's kind of our setup. What's going to also be true, keep this idea in mind, is that just like when I was thinking about the distribution of my sample means, I can look at the distribution of my sample mean differences, right? It's very similar to just looking at the distribution of our sample means. It should be centered around whatever that true mean difference is, right? And then the variance of our sample mean differences should be the variance of that difference variable divided by whatever our sample size is. Just like we had the variance of our sample means was just the variance of the data we sampled from over our sample size. So this is going to be almost identical to what we were doing with sample means. It's just now we're looking at sample differences. Or maybe sample mean differences would be a better way to kind of reference this. So what we were doing before, we wanted to build confidence intervals, looks something like this, where this represented the standard deviation of our sampled means. So, you know, we've got the sample statistic we're looking at. We're going to either use this Z or T distribution, and then you multiply it. This kind of represents how many standard deviations away you want to go to the left and the right. Well, if I want to go 2 standard deviations to the left and right, I need to multiply 2 by whatever that standard deviation is of the statistic I'm interested in. So when it comes to sample differences, we only have a sample variance, right? So we're still using that student T distribution. It's just now, right, things look a little bit different, but it's really like, once we plug the numbers in, it's going to look identical to what we were doing before. For one population examples, where we're looking at a sample mean, but only have a sample variance. Okay. Any questions on that? Is that easy enough to read up there? So it's a little bit, I feel like it's a little bit, I don't know where they have the remote. Let me see if I can, I don't know if it's going to work if I go to menu here. Does that help any? Well, if you can't read something, let me know. I know it's for some reason it looks a little fuzzy to me as well. I'll try to write big. So, let the screen catch up to us here in class. All right. So, you know, we can find this difference variable. We can then find that mean difference, the variance. We've got our, you know, set up our confidence interval equation. So it's really look identical to what we were doing before with one population mean examples. And our degrees of freedom goes back to being easy. It's just n minus 1 because we really only have one population, right? It's the same 10 workers, okay? So, you know, maybe we collect all this data. We get the mean difference is 8.5. The variance of that difference variable is 121. If I wanted to build a 95% confidence interval, how would I do this, right? Well, remember, for a 95% confidence interval, our alpha would be what? Just 0.05. We'd have half of alpha in each side. So remember, we want the t value that gives us half of alpha on each side. So 0.05, think about here, yes. Our alpha is 0.05, so alpha over 2 is 0.025. Our degrees of freedom, well, we had 10 workers, so 10 minus 1. So we're going to look up the area of 0.025 at a degrees of freedom of 9 on our student T table. So 0.025 and 9. Just get some more practice with that. So 0.025, my degrees of freedom, I need to go way down though. So I can get this all in the same thing. 0.025, degrees of freedom of 9, 2.262. So that's the t value, or that's the number of standard deviations I want to go to the left and the right. And from there, it's just a matter of plugging things in. We had a sample size of 10, a mean difference of 8.5, sample variances, I think it was 121. So really at that point, if I can get this to minimize. Right, it's just a matter of plugging everything in. Once we look that t value up, we have all the variables we need. Okay. Any questions on this? So we end up with a kind of lower and upper bound of 0.6 and 16.3. So with 95% confidence here, kind of the interpretation of this confidence interval is that the average change in productivity, right, the true average change or the true mean change in productivity or the true difference, with 95% confidence, I can say that that's a positive value. So that the average change in productivity was that productivity was positive or that it went up. right? So that's kind of, if we're thinking about production, this seems like a pretty applicable, real world kind of thing that would come up where you're trying to see if you see on average productivity changes across your workers. If you find all positive values, you can say productivity went up. If they were all negative values, we'd say that it went down, right? With 95% confidence, it would go down. Okay. So if we do, if we can do confidence intervals, we can also do hypothesis testing, right? So it's going to look very similar to what we were doing before. It's just now instead of the mean and the assumed true mean, it's the kind of true population mean difference and some assumed true difference that we're going to be using. But we have the same right, left, and two-tailed tests, right? Nothing looks different there. Our test statistical equation looks a little different than what we were doing before. But if we remember what we were doing before, it's going to follow the same sort of kind of process. So we'll take that sample mean, we subtracted the assumed true mean, we then divided by the square root of the variance over our sample size, which we said represented the standard deviation of our sample means. It's going to be almost the exact same thing now, it's just we have the mean difference, an assumed true difference, and now we'll divide by the standard deviation of those sample differences. Right? It's really just notation, right? A little bit different. Now, one thing that's kind of nice is for exam examples and things like that, I'll always use that assumed true difference of 0 still. And then we'll kind of see why a little bit more once we get into Excel, why we'll do that as we kind of work through these examples. But now we've got our test statistic equation. Okay. So go back here. Oops. What would my test statistic be? So I don't think I have anything else here, but what we're going to try to do here is we're going to calculate our test statistics. It's really just a matter of plugging those values in, right? Once we have that equation, we're going to be given everything we need, which is just a matter of plugging those values in. Okay? With that assumed true difference of 0, it makes it a little bit easier. Okay? So we have this test statistic of 2.44. Let's say I want to test for whether or not, well, what do I want to do here? Let's do a two-tailed test because I don't think we have one of those later on. So let's say I want to do a two-tailed test. What would my critical values be? Well, I know they are going to come from this student t distribution. Right? For a two-tailed test, if I'm thinking about, I just want to know, is that mean difference? I'm going to assume it's equal to 0. Or what I want to test for is anything other than 0. So it's like my assumed true difference value is 0 here. So what would the critical, so I've got a two-tailed test, so I would need critical values, for instance, that give me alpha total in the tails. But if there's alpha total in the tails, that means there's alpha over 2 in each tail, right? And I'll have two critical values, one positive, one negative. So I could do this for all the different alpha values, right? I can think about, typically I'd look up 0.1, 0.05, and 0.01. But I need alpha over 2, so I'll look up 0.05, 0.025, and 0.01. Once again, it's just like the confidence interval. Our degrees of freedom would just be n-1, so we'll have a degrees of freedom of 9. Okay. So we'll go to our table to get our critical values. Okay, cool, you guys can see that. So we're going to look at our degrees of freedom of 9. The areas we wanted in the tail were 0.05, 0.025, and 0.0, actually, sorry, I wrote 0.01 earlier. It was 0.01 divided by 2, so 0.005. So when I was writing this out earlier, this should have been 0.005 here, 0.01 divided by 2. So I was just writing things down without thinking, a little bit too quick. So we've got 1.83, 2.26, and 3.25. Those are our pairs of critical values, positive and negative. So let's see if I can remember these. So 1.83, 2.26, and 3.25. So what we're thinking about is we just found these critical values. This is what, negative 3.25, negative 2.62, negative 1.83, and then we'd have the same values on the other side. So 1.83, 2.62, and 3.25. We could think about where our rejection regions are, kind of drawing these arrows into the tails. And just as a reminder, these corresponded to the alpha of 10%, 5%, and the 1% level. Okay. So we've got all our rejection regions drawn out. Now it's just a matter of where does our test statistic fall? If I remember right, it was 2.24. So if we had a test statistic of 2.24, that's only going to be in the rejection region at the 10% level, but not in the 5 or the 1% level. So we would fail to reject at the 5 and 1% significance level and only reject at the 10% significance level in this example. Okay? Any questions on that? So the reason why we kind of have pairs of critical values here is because this wasn't in the slides, but I set this up as a two-tailed test. Okay? Just wanting to know, is that difference anything other than 0? All right. So, that's feeling good. So let's work through one more example, and then we'll kind of look at this in Excel. So let's say we have a similar setup where we have 40 Starbucks card holders, so the same 40 people. We had their before and after calorie consumption after the calories were posted on the menu. So the average change in the calories consumed was 2.1. The variance in that difference variable was 64. We've got a sample size of 40. I want to build a 99% confidence interval, so my alpha would be 0.01. I'll have half of alpha, if we remember. Oh, come on. There we go. If you remember right, we have to look up the t-value that gives us alpha over 2 on each side. So if my alpha is 0.01, I want 0.005. And then my degrees of freedom, I don't have it here, I just have numbers, was n minus 1, right? So I look here, 40 minus 1 is 39. So my degrees of freedom is 39. The area that I want in the tail, 0.01 over 2, is 0.005. It's just a matter of going to our t-table. We want 0.005. So in this last column, degrees of freedom, 39. 2.708 would be that t-value that we plug in. Once we have, I didn't want to do that. Once we do that, we have that t-value, right? It's just a matter of plugging everything in, right? We've got that sample difference, the variance, sample size, and now we have that t-value. Okay? So we're thinking about what this means for us. We just found negative 1.3, I think it was to 5.3 or something like that. So the true mean difference, right, in calorie consumption could be negative. So calories the true average change could have been that they went down. Could also be positive, so calories consumed could have went up, or it could even be that the true mean difference or the true average change is 0. So I can't really say much with this confidence interval. With 95% confidence, I can't really tell you anything. I mean, it could have went up. It could be that the average change is positive, negative, or even 0. Okay. It's kind of how we get the interpretation of that confidence interval. And I know I'm kind of going through this a little bit quick, but once we have that confidence interval equation, and once we get used to looking up those t-values, really the rest of it's just plugging those values in, right? A little bit of computation. Okay, so there we go. So I always like this meme, and it fits in with this example, but you should all watch Napoleon Dynamite if you haven't. It's a great old cult classic. Okay, so we'll keep running with this example and think about if I'm looking at calorie consumption, right? And I might want to test for whether or not after they posted calories on the menu, did it decrease? Right? So that's what I want to test for. So I want to see if the average calorie consumption has decreased or if that difference is less than 0, right? If they've decreased, then the change would be negative. So that's what I want to test for. So that's my alternative hypothesis. The opposite would be what I assume is true, which is that it's greater than or equal to 0. Okay? So I've got what type of tailed test here? Look at the alternative hypothesis. I have a less than sign, so I've got a less than or a left-tailed test. So right away, what should be true about my critical values? Yeah, if I've got a left-tailed test, my critical values are going to be the t-values that give me alpha total in that tail. So because I know this distribution is centered around 0, when I'm looking up low alpha values like 0.1, well, the area to the left of 0 is 0.5, so I know that these critical values have to be negative. If I think about what I was doing before, like I have the distribution of my sample differences, and I was assuming that the average difference, right, if I look at that null and alternative hypothesis, was 0. Well, I found the sample difference that they found was 2.1. Okay, so I found something that was above the assumed true value. So I'm going to be a certain number of standard deviations above that value. So my t-statistic should be positive, right? So right away, I don't really have to go through, if all I want is the rejection decision, I found evidence that actually, if we go back, supports the null, right? I assumed that it was greater than or equal to 0. And if we go back one more slide, when we had the other data, here we go. We had a sample difference of 2.1. So we found something that supports the null, so of course, we shouldn't reject it. Which sure enough, if we just think about, we're gonna have negative critical values, and our test statistic, because we found something above the assumed true value, would be positive. Well, yeah, it's not gonna be anywhere close to the rejection region here, right? So this is kind of one of those easy ones where you didn't even have to work through the whole thing. We would automatically know what that rejection decision should be, okay? But if you wanted to, just for some extra practice, we could calculate the test statistic. I already mentioned we found something that was above the assumed true value, so it's going to be a certain number of standard deviations above. So our test statistic should be positive. So right away, we should rule out A and C. From there, it's just a matter of plugging those values into our test statistic equation, right? And like I said, this goes back to like a one population example, and when we assume the difference is 0, it makes it a lot easier. Okay. Any questions on anything here? We're going to dive into Excel for a little bit. Okay. So, whoops. Let's go. So I've got this blank file open. I've just been saving it as we work along. I've got the in-work one or in-class work one. If we go to in-class data. So I've got it on Canvas up to the point that we've worked on it. I'll replace this after class today because we're going to add some more. So last class, we looked at this male data and we looked at the difference in two sample means when we only had the sample variance, right? We had that really complicated degrees of freedom formula. Well, now we're going to be doing matched pairs. So at least now everything goes back to being able to use the easy degrees of freedom, which is just n-1. So this one's a little different than the examples that we just worked through, but I just want to make you kind of aware you can do something like this. Oh, so instead of time periods here, I've got kind of male and female suicides, and then I have different counties. So it's the same population in the sense that, or shouldn't say the same population. It's kind of like I've still got the exact same counties. So it's not like I have two groups of counties, like one in the South, one in the Midwest. This is the same counties. I just have two different variables. Now, usually this would be like a before and after. Well, for us, we can still do this as kind of male and female suicides, right? But within the same county. So for each county, notice I found this difference variable. So I'll kind of show you how to calculate this real quick. I'm just going to delete all of that. So all I did was go, okay, take my male suicides and subtract the female suicides, okay? I'm then going to go over here. If I get this black, like bolded plus sign, and I double left click, it'll basically fill that in, right? Take the difference for every single variable that I've got, every single observation, okay? So I now have this difference variable. What I can do is find the mean difference by using that average function. Select the first cell, hold Control Shift and the down arrow, or Command Shift the down arrow on a Mac, hit Enter. It'll pop me back up to the top, so that's kind of nice. Var.s will find the sample variance. Once again, Control Shift, Command Shift on a Mac, select the entire thing. So if it helps to kind of label these a little different, this was like the mean difference. This is, I guess, our sample variance. And then we've got our sample size, which we use that count function for. Just count up the number of observations. This should be stuff that we're pretty familiar with, right? Just finding the mean, the sample variance, and the sample size. I'm going to use this hypothesized true value of 0 later on. But before we do that, let's build some confidence intervals, right? So I'm going to put my lower bound here and my upper bound here. Okay. All I'm going to do is use Excel to be my calculator. So just as a reminder, I got it somewhere over here. There we go. Let's see if I can zoom in a little bit. All right, so we've got our confidence interval equation right here. Now, I'm just going to use Excel to be a calculator, but I also need to use it to find this t-value. So I'm going to put it in a different cell. I could put it on one cell, but just so we can kind of see the intermediate steps. If I'm trying to find the t-value that gives me alpha over 2 in the tail, well, I know the area in the tail. I want the t-value. I'm kind of working in reverse or inverse, right? We know we're using the student t-distribution, so t.inv. Okay. I want the area in the tail I know is alpha over 2. Okay, so I select alpha divided by 2, and then comma, with the student t-distribution, I need to tell the degrees of freedom, which is the sample size minus 1. Okay. Now, I could have calculated the degrees of freedom in a different cell if I really wanted to. It's probably not necessary. But when I copy this down, and I want to build 3 different confidence levels, or 3 different confidence intervals at different levels, well, I want the alpha value to change, but I want to keep using the same sample size. So I need to freeze that cell reference for the sample size. I'm also forgetting about one more thing. This is looking at the left side of the distribution. So if I'm looking at a small alpha over 2 value, I'm going to find the t-value that I want, but it's going to be negative. Well, that positive and negative are already kind of built into our confidence interval equations when we calculate the lower and upper bound. So we could use the ABS, or the absolute value, and now we got the value that we want. Okay. Copy this down. I've got my 3 t-values. Now it's just a matter of using Excel to be a calculator. So take that sample mean difference for the lower bound, subtract. How many standard deviations do we want to go below? Well, that's what that t-value represents. And then multiply that by the square root of the sample variance divided by our sample size. Okay. Now, when I copy this down to get my other kind of lower bounds, I want the number of standard deviations, or that t-value, to change, but everything else should stay the same. So I'm just going to go ahead, if I highlight this, hit F4 or Command T on a Mac. Oops. Let's go over a little bit so you can see me. I'm going to highlight these, F4 or Command T on a Mac. Now when I copy this down, notice it keeps the sample mean kind of, and sample size reference is the same. Oops, I'll subtract this or lower this now. But it updates that t-value. Okay. Questions up to this point? You want to see a cell again, or? It should look, I mean, we've been doing this with a lot of different examples. Like, the process is really the same. So now I've got my lower bound. I'm going to copy this, hit enter to get out of the cell. I'm going to paste it. And the only thing I need to change for the upper bound is I'm adding that margin of error instead of subtracting it. Copy this down. Oh, copy this down. Forgot my mouse today, so I'm a little bit a little slower than this. So now I've got our upper and lower bound. We can kind of think about the true difference is any value in this range, right? We don't know which of those values, but with 99% confidence, I can say the true difference between male and female suicides is somewhere between 41.7 and 47.5. So even if I'm doing a one-tailed test, if I'm thinking about saying, could the true difference be 0? Well, the confidence interval is telling me, no, it's pretty far away from 0. So we can probably imagine I'm already going to be rejecting this assumed true difference, but we'll just go through the procedure, okay? So first off, I want you to be able to see this on the Excel slide. So I'm going to say that we're going to see, is that true difference? We're going to assume that it's less than or equal to 0, which makes the alternative hypothesis that it's greater than 0. So I want to be thinking about here, we're going to be looking at a right-tailed test, okay? Well, our test statistic equation, that's really just using Excel to be a calculator, okay? So if we go back, got it somewhere. Where was it? Oh, it's right here. All right, so our test statistic equation is right here. So our numerator is going to be, take that sample mean difference, subtract the assumed true difference value. Now it's 0, but I'm going to change it here in a second, and then divide by the square root of that sample variance divided by that sample size. So the test statistics really just using Excel to be a calculator. There's no built-in function, unfortunately. Okay. So I hit enter here, and I get a pretty large test statistic, right? I am 39 standard deviations away from that assumed true value. That's a lot of standard deviations. Now, if I want to do something like find my critical values, right, I can actually use these same 3 alphas. So I'm actually just going to copy and paste these down here. So here's my alpha, and I want to think about finding the critical value. Well, my critical value should be what sign? If I've got a right-tailed test, they should be positive. Now, I can find, when I'm finding a critical value, I'm really just finding either a z or a t-value. In this case, we're using the student t-distribution, so I want a t-value. I know the area I want in the right tail is 0.1, so I'm still going to I'm going to use that t.inv. The problem is if I tell it I want an area of 0.1 in the tail, comma, at degrees of freedom, which is the sample size -1, the issue with this is that it's going to be looking at the left tail. It's going to be looking at 0.1 in the left tail. So it'll give me the right value, but for a right tail test, it should be this value but positive. So one thing I can do is I could just take the absolute value, or if I think about this visually, probably the way to do it that would line up more with the correct way of thinking about it is if I found if I wanted alpha total in my right tail, and I'm looking for the critical value that would give that to me, I could tell Excel the area to the left, and I would know that that would be just 1 minus alpha, right? So instead of like just taking the absolute value because I know it's a right-tailed test, if I do 1 minus alpha here, I get that same value, but positive, right? Because it's a symmetric distribution. Now, when I copy this down, similar sort of issue that with the confidence intervals, I want that sample size reference to stay the same. So I'm going to put $ in front of that. Now I can copy this down and I get my 3 critical values. Notice if I were to plot these and then like think about the rejection region, 39 is going to be way off in that right tail, easily in the rejection region. So we're definitely going to reject here. We could also kind of set this up and try to find the p-value. Now, doing this with the student t-table, we're limited, right? It only gives us 6 columns, 6 different areas in the tail. But with Excel, we're not limited. So essentially what I want to do when I'm finding my p-value is I saw a test statistic of what, 39? The p-value would be the area to the right of that. Okay. So what I can do in Excel is I have that t-value, that test statistic, and I want to find the area to the right. So now instead of using t.inv, I use t.dist. Okay. Now I tell it the t-value, comma, my degrees of freedom, which is my sample size -1, comma 1. This will give me the area to the left. I want to then subtract that from 1 to get the area to the right, and that's my p-value. Okay. Any questions on this before we keep going here? Okay. So it looks like it's a pretty much 0, right? And that makes sense. I mean, the area to the right of 2.2 is, or whatever it was, is 0.01. The area to the right of 39 is going to be basically 0. So another way you can do this, you might have seen when I was typing in t.dist, there's a .rt option. So it's a right-tailed option. So basically, it just subtracts it from 1 for you, right? So here, I tell it my test statistic, comma, what my degrees of freedom is. Because it knows it's looking at the right tail, you don't need to tell it to be cumulative. It just looks up that area in the right tail. And now it looks like it's giving you something different here. I'll show you by the time we're done with Excel, you'll see that these are the same thing. It's just that when we get a p-value that's so close to 0, those built-in functions round a little bit differently. Like this one, keeps it out to the 232nd decimal point. This one, if it gets out that far, it just rounds it to 0, right? It's so close. Okay, any questions on this? So 2 kind of options. Now, another thing that we could do, just like when we looked at the difference in sample means last class, is we have this built-in t.test. So with the sample means, this is where like I selected my male BMI, female BMI variables. It told it how many tails. It did all the calculations behind the scenes for me and spit out the p-value. So this is even, in the match pairs example, the t.test is even more useful because I don't have to create this additional variable. What I'll do is I'll first select this array 1 is, well, what was the variable I was looking at? Male minus female suicides. So I'll select the male suicides, put a comma. Now, kind of one of the pains is I have to scroll all the way back up. If you have the formula bar, you can see that up here. You could just type things in. But usually what I do is I'll first select the first variable. Well, the second one I know is female suicides. I could select it. It would send me to the bottom. I have to scroll up. But I can see that it's in column I. And I know it's going to be in all the cells that the first one was. So I'm just going to type I2 to I1408. Right? So I'm just going to type it in there just so I don't have to kind of scroll up and scroll down. Comma, I'm doing a right-tailed test, so it's a one-tailed test. And then comma, I no longer am looking at a two sample means, different variances. I'm looking at a matched pairs example, right? The same counties. I'm looking at male and female suicide, so I'll put a 1 here. Whereas on Thursday's class, we were using a 3 when we were looking at the difference in sample means. Right? So what this will do is it'll use that male and female suicide variables. It'll calculate that difference variable, find the mean difference, the variance of that difference, the sample size, compute the test statistic, put the test statistic into that t.dist function for you, and spit out at you what the p-value is. Okay? Any questions on that? And if it's a 2-tailed test, it'll even multiply the area by 2 for you. But here we only had a 1-tailed test. So I hit enter. Sure enough, I get the exact same value. This one also kind of keeps it out to a further decimal. Any questions over that? I want to see that again. Okay. So this should be like the last problem on that Excel homework. This should kind of help you kind of answer that one. Now, one thing I want to point out here that isn't so much relevant to what we're going to do, but if you outside of this class, like I said, I know the marketing upper level courses do this sometimes, but like they do these t.tests. This is what they're talking about, t-tests, right? And this t.test built-in function is pretty helpful. Now, one flaw of it, and the reason why I show you how to kind of go through this step by step instead of using that t.test option, it's like, well, why? It's a lot easier. Why can't I always just use this? Well, basically what we found here is we have a really low p-value. So if I'm thinking about making like my rejection decision, I could use that if function to say, okay, if my p-value is less than alpha, comma, put the word reject in, comma, if it's not, then I failed to reject, right? We've done this before. I'm going to let the alpha change so I can look at different levels. I want to keep that p-value cell reference the same though, so I'm going to freeze that. And with a p-value of 0, it's going to be less than all of my alphas. I should be rejecting at every level. So what I'm saying is I can reject this null hypothesis that the difference, the average difference across these counties between male and female suicides is not less than or equal to 0. I'm rejecting that. Well, can I reject that it's less than or equal to 20, right? That the average difference in male and female suicides is at least 20, right? So I put 20 in there. I still have a really low p-value. Well, what about, so I can still reject, I can say that the difference is not less than or equal to 20. It has to be greater than that. What about less than or equal to 40? Let's try and change it up here. Still, I can even with 40 reject that the true difference is less than, it's something above 40. I think once I get to 41, no, maybe not, 42. Yeah, there I start to fail to reject the null that it's, less than or equal to 42 at the 99% level. Okay. Now notice my p-values have been updating this whole time, but not for that t-dot test. Why? Because that t-dot test, there's nowhere, right, in this function where I tell it a hypothesized true value. It always treats it as though the hypothesized true value is 0, right? It can only deal with 0. Anytime you want to use anything other than 0, you're going to have to kind of do this, do it all out, I guess, the behind the scenes work so that you can actually get the correct p-values here. Okay. Any questions on that? Otherwise, we'll probably get out of Excel here for a little bit. All right. So we're kind of going to do hypothesis testing, but kind of not. I'll mention some stuff related to hypothesis testing just so we can connect the next topic to what we've been doing. But really what we're going to start looking at is, we've really focused on one variable. And once we got to the two population stuff, we started to get some interesting questions, like, is there a difference in male and female salaries, at the same position or at the same job? And we're starting to try to get at, like, testing for whether or not things, I don't know, making some real statements. What we haven't looked at is, like, well, how are multiple variables related to each other, right? Or how are they correlated? We talked about this a long time ago where we had measures like the correlation coefficient, right? So it's trying to pick up this idea that, if I see a correlation coefficient or a covariance that's positive, that tells me that as x goes up, y also tends to be higher. Or that as x is lower, y, if they're working in opposite directions, and as x gets higher, well, then y tends to be lower, right? So they can kind of see this positive negative relationship, or maybe that as x goes up, y doesn't really change at all. So this is kind of just a quick review of that correlation coefficient. We're not going to really use it too much, but this idea of looking at the relationship between two variables, we're actually going to write out a better measure of that, okay? So that correlation coefficient can't pick up certain things, and what we want to really do is test for whether or not there's a kind of linear relationship between some variable x and some variable y. We can think about the most simplest way, or kind of think about this in the most simplest form first. What I'm doing is I'm looking at this variable x and this variable y. Okay. So we're going to kind of get to this idea of running, using a simple linear regression. Well, let's say, I don't know, x is income, and I don't know, y is, we could do, I don't know, something like, well, that doesn't make sense. We'll do income as the y variable, and maybe education, like years of education as the x variable. Right? This could be a real data set. Well, then every observation, I could take that person's years of education and their income and plot them. I then go to the next observation, take their years of education, their income, plot that. I would then do that for every single observation in my data set. And I could think about, I would have some scatter plot, right? With all my observations that were plotted out. From there, if I could use that data somehow to get this line of best fit, so I want to try to draw a line that best fits the data. If I did that, I would then have some intercept A, and the slope, if I think about kind of rise over run, the slope of this line of best fit would be B. So we're going to call this that. If you were to tell me any X value, like 10 years of education, if I could get a value for A and B, I could come up with a pretty good prediction for that years of education where your income would be, right? I can start to come up with predictions. This is the general idea of what we're going to do. Well, we're going to have to talk through, how do I get this line of best fit? I have the data, right? I have all these observations. How do I get that line of best fit? So with that idea in mind, we're going to have some terms that we got to get out of the way first because I'll start using. So anytime I talk about this y variable, so when we're thinking about that line of best fit, anytime I talk about this y variable, this is the dependent variable or the left-hand side variable, right? So y depends on x, right? So y is the dependent variable. X is then going to be our independent variable, right? Well, come on. It's what we're using to try to predict y or to better understand the values of y. So y is dependent, x is independent. We're then going to use regression analysis to basically come up with what should that value for a and b, the intercept and the slope of that line be, right? So this is regression analysis is what's going to allow us to get estimates for what that intercept and that kind of slope is, right? So, we think about this. If I've got this formula, I already kind of did this by hand, but, if I've got the scatter plot of data, I could draw a line of best fit and come up with a value for the intercept and a value for the slope, right? If I think about different relationships here, if I had a pretty flat line, what would my slope, what would that value for B be in this case? If I have a flat line, then as x goes up, y is not changing at all. I'm guessing someone's getting here, right? 0, yeah. I'll have this slope of 0. If we go back up, oh, come on. All right. A positive linear relationship, the sign of my slope would be positive. That as x goes up, I'd be adding more to that predicted y value, right? If we have a negative relationship, we would think the slope there would be, so b would be negative, right? A negative relationship, we're going to have a negative slope coefficient. Okay? Now, we're not going to do, if I somehow have a little bit extra time, I might show you what this looks like, but I'm not going to ask you any questions on it. But we could actually even start to do things like, if you were pushed into statistics outside this class, like I think it's 321 and 424 advanced stats or econometrics, you'd start to talk about things like, well, what if the relationship isn't linear? What if I plot my data and it looks like it's a nonlinear relationship? We can actually estimate that as well. Like I said, I might be able to show you an example of this, although I won't ask you any questions about how to do this. So we're going to focus on just linear relationships. So what we're going to do, the way we're going to come up with this line of best fit is you can think about, I had that equation written earlier that y is equal to some intercept value plus the slope times x. So there's also for every actual y value we see, if I'm just using, say, education to predict income, there's a lot of other things that influence the income that someone makes. All those other things are going to be captured by what we call the error term. So this is epsilon or the error term. If I try to predict, Bill Gates' income based off his education, I'm going to be wildly off. Some observations, this epsilon would be larger. For other observations, it would be smaller. But when I was coming up with that line of best fit, notice I don't have an epsilon here, right? So anytime I come up with a prediction, we'll call this y hat. So anytime I don't have that error term, right, all I'm doing is predicting y based off of the years of education, we'll call that y hat, and then the actual y incorporates that error term. Okay? So you can kind of think about, well, let's see how I figure how I go up with it. Yeah, so we've got y hat, right, as the predicted value. So I can think about, oops, if I rearrange this a little bit, y is really just the predicted y plus the error term. Okay. So let me see if I can give you a visual. I think I've got some slides here, but I think we can set this up pretty nice. So think about this as, right, I come up with some values for A and B. I can predict income for every years of education, but for any one observation, like let's say this guy right here, right? Whatever, maybe this is 12 years of education. So for this individual, if I come up with their predicted y value, it's going to be somewhere up, it's going to be on that line. Their actual y value is here, so we can kind of think about, here's the error, right? Now, for this observation, we found an error that was, well, I predicted it was too high. So if I take the actual y and subtract the predicted y, I have a negative value. Well, it's maybe for like an X value up here, you know, right here. So for this observation, here's the actual Y. Here's the predicted Y on the line. So now here I would have an error term that's positive, right? So for every single observation, I could figure out what this error term is, right? What was the difference between the actual and predicted Y value for every single observation, right? If I do that, I'll have all the errors that I'm making. So the statistical, if I can get there we go. So I kind of already drew this out, right? We've got positive errors, we've got negative errors that we can make for every single observation. So how are we going to actually get the A and B value, right? How am I going to figure out where this line of best fit is? I'm not eyeballing this, right? I mean, I was when I was drawing it, but like the actual values we're going to use, we're not just eyeballing it. So how can I find the best A and B? How can I find the best values for the intercept and the slope where I best fit that data? Well, what we're going to do is say we're going to minimize the sum of the squared error terms. So you almost think about like a real easy way to think about this is I want to choose a line such that if I added up all these error terms, I'm making the smallest amount of total errors possible. You know, if I have a line that's, you know, way up here, I'm going to have you know, if I add all the errors up, they're going to be huge, right? Because I'm way off of the data. If I choose a better line, right, a better A and B value, if I add up all those error terms, it's going to be much smaller. So I want to try to get this line to use an A and B value such that the sum of the errors are as small as possible. Now, I go a little bit further where we square the error terms. So it's kind of similar to the variance. First of all, if I square these error terms, well, if I were to try to add them up before, some were positive, some were negative. By squaring them, I don't care which direction my prediction was off. I just care that I was off, right? But also by squaring it, what's this going to do, similar to the variance? Let's say I had an observation way up here. Really, really large errors are going to be over penalized, right? Because like if I, you know, I'm off by 1 squared is 1, but if I'm off by 2 squared is 4, right? So it amplifies kind of these extreme errors that might be made with my predictions. Okay? So I'm just going to write the error term, which is really it's just the difference between the actual Y and the predicted Y. I'm going to square that. We could go through the math. I'm not going to kind of bore you with it, but basically you would have this equation where I can write out what the predicted Y value is. I take a derivative in respect to the two things that I'm trying to get an estimate on, A and B, right? So I take a derivative in respect to A, set that equal to 0, take a derivative in respect to B, set that equal to 0, two equations, two unknowns. This is kind of going back to some calculus stuff. I'm not going to expect you guys to do this. But the long story short is, right, you don't have to know how we get to choosing A and B, but we can, right? So we have two equations, two unknowns. Let me keep going through here real quick. Oh, I repeated slides apparently. So I've, you know, two equations, two unknowns. We end up getting, here's our formula to solve for A and B. Now you can imagine I could probably do this in pieces in Excel. I don't think I'll waste time going through it. But you can imagine if I had the X and Y variable in Excel, I can find the average X and I can find the average Y pretty easily. I could then create a column where I look at the difference between each observation's X value and the mean, and each observation's Y value and the Y mean, multiply those two in a different column, you know, add, you know, square that difference in another column. Like I could break this up into parts and do this, okay? Now, like I said, we don't have to understand exactly all the math, you know, taking those derivatives, set them equal to 0, that got us to this point, but we need to know that we can find these A and B values using these two formulas, okay? Sometimes, you know, another formula might look something like this. It's just rearranging this. Like I said, I don't think I'll probably waste time showing you how to do this in Excel because there's a much easier way to do it. And really when it comes to linear regression, we don't want to waste time on the computation. We really want to be able to do a good job of interpreting the results we see and applying them. Okay? So I'm going to skip this slide because I'm not going to kind of have us do this. I kind of want to show you how we would do this in Excel today. So I didn't think we'd get this far. So I don't believe I have the data set up on Canvas yet. I'm trying to think if there's some old data we could use. I'll upload one here right now. So I think I should have my stuff from fall. I'll go back here. Oh, that's not it. Why am I not seeing? Oh, because I'm in Google Drive. All right. Give me 1 second here. Sorry. A little bit of a interlude. I should be able to see. There it is. I've got COVID data. I think the one I wanted to do was Gpa data. So I'll get this up for next class. We'll just kind of introduce this idea because I really just need a data set to show this to you. So when I go to my data tab, there's a data analysis option right here. It's likely that that's not in your Excel yet, okay? Maybe if you've in other classes have added it, but what you need to do, and I think it's a little bit different on a Mac. So the first thing I'll say, I'll go real slow so we can get these steps on. So I would go to File and then Options. I forget exactly, there's a slightly different way of getting to the options in on a Mac sometimes. I think it's under the Tools tab. Because then once you go to this Options, you'll see this kind of tab that's Add-ins, right? Like I said, I think it's under the Tools on a Mac. So once I'm at Add-ins, I'm going to manage my add-ins and make sure that this analysis tool pack has a check mark on it. Or if it's slightly different on the Mac, I think sometimes it just asks you, it prompts you to click on the analysis tool pack and kind of add it in. Right? So once you have that, you have this data analysis tab. So I would, you know, I'm going to post an Excel, last Excel assignment. Like I mentioned, you know, if you already are happy with your first 4, and I'll try to get those 4th ones graded as quick as possible as they're coming in. You don't have to do the 5th one, but if you did, it would replace your lowest. I think it might be a little bit easier. But one of the main component, you know, in order to even start that assignment, you have to be able to get this data analysis option in there, right? Yep. So if you have a Mac? Yeah. So if you open up Tools, Add-ins. Yeah. So if you look at Add-ins, it should have a, oh, it just says data analysis? Yeah, that should be the one you want. That's probably it. If it says like analysis, so it's the analysis tool pack, it may not say tool pack on the Mac. Okay. Once you add that in, under your data tab, there should be a data analysis option all the way to the right. Okay. Yep. And if you have any issues with that, is there, you know, if those of you who are maybe watching the video after the fact, send me an email so we can make sure we get that added in pretty quickly. So I did some, I don't know what I did here, some goofy stuff. I was doing some average ifs where I was just trying to compare the GPA of kind of males and females, but we could actually, you don't have to do something like that. What we could do is actually look at this college GPA data, and I've got all these different controls. So maybe I'm just interested in what is the impact of, or can I predict college GPA with SAT scores? So I'm going to blow this up a little bit and type that out for you so we can know what we're thinking about here. So what I'm thinking about is I want to try to be able to predict GPAs at the collegiate level, and I'm going to try to use SAT scores to do that. All right. So I'm going to hit enter here. So this is the regression that I want to run. So I go up to my data tab, go to data analysis, see all these different options here. I'm going to go to regression, hit OK. My Y variable that I wanted to use, so I scroll over here, is going to be that college GPA. Right? So I'm going to select the label, hold Control Shift or Command Shift on a Mac, hit that down arrow. Okay? Hit enter. My X variable was SAT score. So I'm going to go over here, select that SAT score variable. Then hit OK. Oh, well, I'll show you here real quick. I want to make sure I told you. Notice I had the labels box selected because I selected the first cell. And I wanted to make sure that it treated that not as a data point, but as the actual labels. Right? So once I did that, it'll spit this regression output on a different worksheet for me. Okay. So first thing for now, we're not going to focus on any of the stuff that's up here. Notice it does identify how many observations you had, which is kind of nice. But the main thing we're going to focus on is this coefficient. Okay. So that value of B, we're going to start calling that the coefficient. Okay? Because it's telling me what the relationship is between my X and Y variable. Now, what's going to end up being true, and this is maybe jumping the gun a little bit here. Let me see where it was at in the slide so I make sure that I'm not doing this wildly out of order. Okay. We'll stop share. I want to kind of give you an idea about what's going on here. So we're trying to come up with these values for A and B, right? So what we're actually doing is we're coming up with predicted values for that coefficient, right? There is some true population B value, right? There is some true relationship between that X and Y variable, but we're just getting an estimate using our data set of that. Well, just like sample means or sample proportions, as long as that central limit theorem is met, and at, sample size of 30 or more, my sample coefficient or sample slope estimate will be distributed, normally around whatever the true relationship, that true slope should be between that X and Y variable. So, you can think about, I can come up with things like test statistics. So I would take the sample statistic I'm interested in, subtract the assumed true, and then we're going to divide by something that kind of represents our standard deviation. So you can think about the standard error is like the standard deviation of our sample coefficients, right? Or our sample slope estimates. So we're going to be able to do kind of a similar thing. Now, we're not going to have to do a lot of this by hand, but one thing that ends up being true is we always assume that the slope value is 0. We always start out assuming there's no relationship. So you can almost think about the null and alternative hypothesis we're always going to have for that true slope coefficient. We're always going to be trying to find if it's something other than 0, so we start out assuming it is 0. So every single time we do a hypothesis test for these slope coefficients, it should be a two-tailed test. We only have kind of a sample variance or a sample standard deviation, so it's going to be coming from a student t-distribution. Okay. Now, like I said, we're not going to have to worry too much about finding test statistics and calculating p-values. I probably will have you calculate test statistics. I should say that again. But I'm not going to be, finding the p-value is going to be a little bit easier because if we look at this Excel output, so that coefficient was the estimate for B, right? That's our slope estimate. So if you want to think like that coefficient really represents, and I'll call that B hat if I was writing this out and taking a little more time, right? B with a little caret above it because it's our estimate for what that slope would be between our X and Y variable. But notice it gives us a p-value for these coefficients. So I have the estimated intercept coefficient, the estimated slope coefficient on the SAT score variable, and I have the p-values associated with each of them. So I could see, right, some coefficient value that's different from 0, but right, if my sample size is small, my sample size was small, even if I see something that's kind of, a little bit further away from 0, it's still fairly likely. So I can do the same approach where once I find that slope coefficient, I turn it into a test statistic. I then kind of find the area in the tail, multiply it by 2 because it's a two-tailed test, and say if I can reject the null. If I can reject the null, what am I rejecting? I'm rejecting that there's no relationship. So when I look at these p-values, they're basically 0. E to the negative, remember, means move that decimal 166 spots to the left. So this is basically a p-value of 0. So I can say that these estimates, right, are significantly different from 0. Or I can reject that null that that coefficient, the true population slope value is 0. I can reject that. Okay? So we want to get low p-values here so we can reject that null, which is that there's no relationship, and say that we found pretty strong evidence that there is a relationship between the SAT score and the GPA. Okay? Now it's positive, so that's telling me that as SAT scores get higher, GPAs, predicted college GPAs would also be higher. So that kind of makes sense, right? The intercept, well, we'll talk about that a little more in a second here. Okay. So that's how we would run that regression in Excel. Oh, that's not the right file, sorry. That's how I run that regression in Excel, get those slope coefficients, and you kind of start to think about, we really can do hypothesis testing with them because Excel is also going to find those p-values for us. For the sake of what we're doing, you can kind of ignore these. These are really like just building a confidence interval for where the true coefficient is, which is kind of interesting. But for the sake of this class, we'll primarily kind of just use that p-value and the coefficient value from this regression output in Excel. Okay. Any questions on anything I said there? So I think I'll kind of end with one more thing, which is we want to start interpreting these coefficients. So if I come up with these estimates, so let's say, I figure out what my slope coefficient estimates are here, right? I get this from Excel. I get these two values, right? Well, I could then start to make predictions for any value of X, right? Well, think about what the meaning of this slope coefficient is. What this is really saying is that, okay, if X goes up by 1 unit, then B is the predicted increase or decrease in our predicted Y variable, right? Because if X goes up by 1, like think about it this way, right? If I took B hat times 1, I get B hat. If I get B hat times 2, I have 2 times B hat, right? It's B hat higher, right? So for every 1 unit increase in X, my predicted Y value is going up by whatever that slope coefficient I get is. Okay? So if we think about the interpretation of the regression we ran, how is SAT score measured? In points, right? So when you think about the interpretation here is a 1 point, well, let me type out the general one. So a 1 unit increase in X would cause the predicted Y value to either increase or decrease, depending on the sign, by whatever that coefficient value is. This is kind of our general interpretation. A 1 unit change in the X variable would cause the predicted Y value to go up or down by whatever that coefficient value is. Okay. So here I get 0.0019. Well, 1 unit increase in SAT would be 1 more point on the SAT would cause predicted GPA, or the predicted GPA, I guess, if I'm going to be grammatically correct here, to increase by 0.0019. Now, it might seem pretty small, but it's 1 more point on the SAT score, right? If I'm looking at somebody who has a 1200 or a 1201, how are they that much different, right? But what starts to get interesting is, well, if this is a linear relationship, if I know the impact of 1 point, I can find the impact of 100 points pretty quickly. So the coefficient interpretation is always just for 1 unit, in this case 1 more point. But let's say I wanted to know what the impact of getting 100 points higher. So let's say I'm comparing somebody with a 1200 versus a 1300. Well, if this is the effect of 1 more point, I could actually just think about multiplying that by 100. So if I see someone that scores 100 points better on the SAT, their predicted GPA would increase by about 0.2. Well, 0.2 is not anything to, it's not the biggest increase in GPA, but GPA is only from 0 to 4, so a 0.2 increase is decent. It's a pretty large, sizable effect. You could think about, well, what if they were, 200 points higher? Well, if I know the effect of 1 more point, the effect of 200 is just 200 times that. Right? So we could start to think, yeah, the interpretation on this coefficient will always be for 1 unit. But once we know the interpretation in terms of one unit, you just take that and multiply it by whatever number of units increase you're interested in. Okay? And we'll go through more examples and review this kind of next class, but I just want to kind of introduce this with a kind of a simple idea, SATs and GPAs. So I'll put this GPA data up on Canvas when I get back to my office today. I'll also put up an online quiz that has a little bit of matched pairs that needs to be done before we meet on Thursday, before we meet in class on Thursday. Other than that, I think that should do it for us today, unless anybody has any questions. I'll get out of here. Okay, I'll also get those practice exams up for the final. I might not be taking a look at them quite yet, but if you want to, I'll get them up there as we